Well, thank you very much to you, Valerie, for this so kind invitation to be here. I'm both very proud to be invited and nominated, as you said, and also very happy because I know a lot of people, good friends here, and it's always a pleasure to come to Novosibirsk, either in winter or in summertime. And I realize that this summertime will be very good because I arrived, not everything is hot and so kind here. I cannot imagine there was so much rain last week and last period. So I was asked to speak a little bit about modern trends in heterogeneous catalysis. So I tried to do something about the trends, the new trends, to go from stochastic research and integrated approaches. Why? Because I remember when I was a young, not student, but a young researcher at the Institute of Catalysis. I just remind you that my institute in Lyon is a little bit younger, only 1 year after you, because we were impressed by this new center, so we decided to do the same 1 year later. And at that period, the director, when I came into this institute, the director was Boris Imlik, and he used to tell to the young researcher, look, the good thing is not to go under the light of the knowledge where everybody is making research, but try to go in the darkest places to find there is so many things others to discover. So this, and the fact was that everybody was trying to go in dark region of the knowledge of catalysis science, and sometimes it was true, sometimes not, but the result was a little bit scattered and random, and we say stochastic research in all directions. So now if I want to find some modern trends in catalysis, indeed there is new words here as compared with the past, and essentially something which is related to sustainability, circular economy, a lot of things we have to put in the contract because it's so important. And that's probably the driven forces for the modern catalysis. But there is a lot of other things. But anyhow, what to do with this kind of big flowers and big mess as well? So we can think that discovering new trends is kind of being a real art. You can see with the crystal balls to be able to where is the good science, where is the bad science. But indeed, the crystal balls is very important for you to find the money, because without the money we will not have good science. But another way to be more efficient is to make some lobbying. I'm convinced of this. You cannot wait that we will tell you do this and do this. No, you have to be active and participate to some lobbying for the future. That's important. If I take the agenda of the EU, for instance, for the next framework program here, we are here, and we are now starting the FP9 framework program 9. But you see that to reach the further program, there is a lot of different steps which are all very important for this work program definition in 2021, 2022, 2024. We have to anticipate this, because if you are passive, you will only have what has been decided by the others, and that's the key of the problem. So we have to participate in the decision making for the European Commission, for us at least here. not directly your problem, and not for the US, but for all the group in Europe. We have to follow this. And lobbying is also a very complex task, for sure. Because if I consider here this, you see the red dots here? I can use maybe the green. Yeah. If you see this, well, there is one hand this work program, there is so many actions possible with the advisory groups, program committees, so on and so on. So we have to find some ways to be active for this lobbying. So one thing which has been created in 2015 was the European cluster on catalysis. And this cluster has been created with most, if not all, the catalytic group in Europe trying to think together and to determine some priorities for the future in order to push a little bit this lobbying towards industry, for instance, because industrial companies are so important to decide for the future. And so to identify the challenges, the synergy between stakeholders, academia, and so and so, and promote also approaches, integrated approaches at the EU level. And this cluster made, as usual, a new roadmap which has been created based on existing roadmaps, like the German roadmaps. There was something in France and so and so. But to try again, and this document is available here on this So I picked some priorities from this roadmap and to convince those who will decide about the future calls and programs where the money will allow those groups in Europe to work correctly. So, for instance, biodegradable resources and recycling of domestic waste is a very, very important topic to work with. Dealing with diversity and viability is important also. Energy and carbon-based integrated catalytic processes, and promote process intensification. So we are close to engineering, macro engineering for the future, and so on and so on. Another one is catalytic transformation of light hydrocarbons. Again, because we have worked since a long period on light hydrocarbons, but there is a renewed interest for this due to for instance, the new resources on biomethane, for instance, or the light gases in the refineries which can be transformed and transformed to make some monolithic or butadiene with those light gases. Also, stranded gas and shale gas, biogas, even if the shale gas is not exploited yet in Europe, there is some push to work on it and not to be ready when the shale gas will be European, to have some good argument for this. And also scalable catalysts, well, that's the usual path of increasing the quality of the product. There is another important push towards artificial photosynthetic devices. What is important is that from this list, short list here, if I check the calls which are now published, we find most of these words are now in the calls. It means that this kind of lobbying together with the CETIC, which is an organization of the chemicals industry in Europe, have been efficient, and we find now in the official text from the European Commission, we find this kind of orientation. Now, the next job is to write a good proposal and to find a good consortium, putting together big guys, end users, industry, and small guys like academic groups. But we have made our test. So some other points we might consider also is if we check a process from the reactor to the usual active particles, this is a downscaling process. It's important to have a kind to control all these aspects of this downscaling and for the result, and then to make upscaling again from knowledge obtained here in this area to be more efficient for upscale to a real world. I take another example, for instance here, to illustrate a so-called value chain. We start here from black liquors, which can be collected from the pulp industry, which are not completely used, and we have lignin also, which is available, low quality lignin, not craft lignin or not organosolved lignin, but low quality lignin, which is very, very abundant, and together with a kind of hydrothermal liquefaction, we get some bio-oil which has to hydrotreat, and then we can make some co-refining to make some hybrid biofossils. So this is typical, the scheme of a so-called value chain, and those programs, they ask us, you have to analyze the full process from scratch to the end, to the product, and also during 4 or 5 years together with those consortia, you have to increase the so-called technology readiness level from, I would say, academic level to something which is close to which is a demonstration, industrial demonstration, just below the demonstration. And this is the content of those new projects. So I will have I will just make, this is first, means that there will be a second, and if I have time, a third one, I will ask you if I have time. Some process integration, because the keywords are integration. So this is something which is very close to the present example, was the inlet of upgraded bio-oils from pyrolytic in a crude oil refinery. I've seen Vadim, we have worked a lot together on a similar approach. So this is the oil refinery, and we can find here, we could think about introducing those oils, bio-oils, either in the hydrotreating, hydrocracking, or FCC units. So we know for the FCC units, because this has been already demonstrated by companies, probably in Russia as well, but this has been made public by Petrobras, that we have a rather low carbon yield by mixing these bioliquids together with oil distillates. But this has been demonstrated, it's feasible. You can do it at least for a short fraction of this added bio-oils we can do it. So we have to optimize those performances, and we have to make a downscaling, check at that scale, and therefore upscale again to demonstrator, DCR or real circulating FCC units. So on the small reactor, we can check that we have a positive impact of adding some 10% of bio-oils, which has been a little bit mildly upgraded. Positive impact on conversion, gasoline yield, and we have lower light gases production. But we have negative impact with coke formation increase, which is a major issue, and some problem with the gasoline quality, more aromatics in the phenolics. So we have to explore some strategies how to deal with those bad impacts. So we have to optimize upstream by hydrodeoxygenation, decreasing the oxygen content of those biooils, and increasing and optimizing the process conditions, and also working on the FCC compositions, of FCC catalyst composition. This is a kind of way to tackle several problems together and try to see what we can do together. So I will just give you some words on the third one. If I consider usual FCC catalysts, both the real industrial catalysts with the matrix and the zeolite crystals in it, and the zeolite structure, both essentially Y zeolite indeed, and a little bit of CSM. For instance, we have very different composition in terms of porous volumes between micro and meso-micro systems. The problem is that with those biooils, we can see the mesoporosity here, and we can see that all this mesoporosity is blocked by coke when we are making those co-feeding. And we can understand this from this scheme. This is the zeolite, the Y zeolite unit cell, and those lignin fragments cannot enter, indeed, they are too large, too bulky, and so they are transformed, all this chemistry here outside, together with the protons, for instance, coming from the light hydrocarbon molecules, but the trend is to form coke outside the zeolite, in the mesopores and possibly in the macropores. Essentially, the mesopore, either thermal process coke or catalytic process. So one of the basic ideas, we have to create more mesoporosity to make easier the penetration, the fact that those bulky molecules can enter and react within the So this can be done by this kind of nice chemistry with where we start from the initial zeolite, here it will be in red, and we transform it with CTAB into zeolite with some holes in it, and we can see increase of the mesoporosity here, 0.17, 0.27, 0.50, but also a slight decrease of the microporosity. We change also indeed Lewis and Bronsted acidity in reverse ways by making these deoxidizations treatment. And we can see that if I check the naphtha yield on the coke yield, what is interesting is that we can see that the naphtha is increased here for a kind of mild mesoporosity, while the coke is decreased here again for this kind of optimum in the middle, or not too high mesoporosity, because we are touching both the Bronsted and the Lewis site for those who are familiar with the acidic chemistry. And we are also touching the phenolics. We are decreasing a lot the production of oxygenate. This is done from phosphorus NMR, and you can see that the phenolics are much decreased with this dealkalization, this treatment. So we can see that for the value chain analysis, we can optimize different things like, I haven't seen this is just a result. My hydrotreatment gives the best yields. We can increase up to 30% the percentage of added biooils. and we have improved the octane number and piona in the products, and we have seen just now that by this intermediate calculation we can get good test naphtha yields and quality. And now what is in progress. So from all these trends, we try to collect them together and to validate at pilot scale with companies like oil companies which are in those projects to validate at pilot scale the optimization of this before going to the real refinery. So, yes, I should have some time now for a second example. Here, this is completely different things. Can we start? That might be also a good trend for the near past and the near future. The problem, the dream of the researchers in catalysis is to be able to predict what will happen if I take this catalyst for a complex reaction. Can I predict the behavior of those systems to avoid a very costly period where we have to test everything? So this is the idea of this research, to look for predicting tools for increasing, making speeder the research from the idea to the application. So, and here we are using the high-throughput screening and statistical model. This is a study which has been done together with a. So I start with a so-called rather complex reaction. And this reaction is a bifunctional linear alkanes over C10 to make dehydrogenation into linear alkene benzene, for instance. So if I start with the paraffins here, those linear paraffins, you can have some dehydrogenation in olefins, diolefin, triolefins, which can be recombined through cycloparaffins or cycloolefins into the aromatics. This is target product. But together, we can also have some isomerization of those paraffins, and part of those products can be cracked in smaller units and lead or condensed into polymers to lead to coke. So the main product in this complex system is olefins, aromatics, and cracked C10- when we start using it. So here the letter A is related to the acidity of the catalyst, and platinum is related indeed to the metal sites because it's a dual chemistry. So the idea is to start with more simple reactions. One is typical of the metal reaction, autoxylene hydrogenation, and another one is typical of the acidity. And here we make butene isomerization, 3,3-dimethyl butene isomerization. And the idea is to work on these catalysts, on these reactions, to rebuild a kind of predicting so-called QSAR, quantitative structure activity relations. So we start from a large library, existing library of catalysts with a number of metals, and together other products which are in general considered for those industrial catalysts, which makes a library with about 100 catalysts. Those, and then after we use so-called parallel reactors. Here, this is one has been built in our group with the tech company, and the other one has been designed by Avelino Corma, and also with this same company. So if I take the first simple reaction, monofunctional reaction, which is sensitive to rather weak acidity, here we have this isomerization, between isomerization. We can have a very simple kinetic equation related to the mass of catalyst, the transformation, the degree of transformation of the product, and this is the pressure, partial pressure, initial partial pressure. And so we can describe the acidic function of the catalysts, which are tested, from the rate of transformation, the rate of isomerization of this reaction. So we can rank most of the catalysts. Here, this is a log scale, so we have from almost 5 or 3 orders of magnitude. And in black, this is support alpha, theta, alumina, and in white, this is delta alumina. You see a very important effect. And also, we can see also effects of the metal. Here, the white zone around palladium and platinum, and the black zone with rhodium and as more or less expected. So, from the simple kinetics, we can have a first descriptor. The rate of this reaction starts to be a descriptor of the acidity of the phase. The second simple probe reaction is orthoxylene hydrogenation. And here, this is more or less the scheme of this reaction. And this is sensitivity both to metallic composition, like platinum, palladium, you see the difference here, and the acidic features. Again, we have to model this simple reaction with empirical processing based model here. And in this equation, we have a number of kinetic descriptors, all the constant or equilibrium constant, the orders, the activation energy, and the two exponential factors. All these factors starts to be descriptors for the reaction. So we have more or less 10 kinetic parameters, which is interesting, but which is too high a number. So we have to reduce that number for the model. So first we can see the parity plot. So the model is okay for the different systems. That's an example. And we have to reduce the number of kinetic experiments, because if we have, depending on the number of tests we would have to do and the number of experiments, you know that all those who are specialists in kinetics, we don't have to have a too high number of kinetic parameters, because it starts to be very artificial and very difficult to extrapolate for other cases. So we do that so-called principal component analysis. It means reduce the number of parameters of kinetic parameters to 5, 6, or even better, three principal components, 3 parameters, which will be a kind of gathering of all redundant kinetic parameters. This is the usual statistical treatment, nothing special to do with this, but we see that all these parameters are very close on a statistical point of view, so they could be merged together. And this is the effect of this statistical treatment. And also after that, we can see the catalyst mapping, those who have been tested for this reaction of the hydrogenation. And we see that we can check the variety and the way that the different catalysts are scattered in those PC2 and PC1. Here, so there's only two parameters considered. Here, the principal component. So the next step is we have now everything is ready from the two model reactions. we have to go to the complex fraction. So we have to acquire the kinetic data for those, for testing those catalysts from the library with the complex reaction. And after that, we have to look for this quantitative structure-activity relationship with the model parameters. So I remind you for the complex reaction of dehydrogenation, we have the three main targeted products, olefinols, aromatic and fraction. So we can have those kinetic expressions and we can measure the initial rates. And we establish this famous statistical relationship, which is a predictive tool from, this is the performance of the complex reaction, and this is the different kinetic parameters or descriptors, which have been reduced for some of them to a number of principal components. And this is the final results. This is the so-called validation of this Q SO. You see that there is some outliers, but for olefins, we see that all the predicted performances of the catalyst for the complex reactions are rather well corresponding to the experimental value. So we are in a rather good efficiency of this Q SO and predictive tools. This is here, the results are a little bit looser, and for the cracking, it is exact. So, again, this is for the future, for the present and the future, a way to save money and time, and maybe to know, this is a message, that for predicting the behavior of catalyst, there is not the obligatory downscaling to theoretical studies. The theory is very interesting, but because theory can predict as well, but here we have a real prediction based on real data. And that makes a big difference. And, okay, I will very fast, you allow me 5 minutes, perfect. Fischer-Tropsch synthesis, another way also for the future to develop new generation of catalysts. It's not completely new, but here this is dense crystals of silicalite, and here this is so-called nanoboxes, where we can extract part of those crystals to make a void volume to increase the diffusion and the reactivity of the system. This is technique, so we try to do that. This is unpublished results, to make those nanoparticles in hollow silicalites together with some iron which has been deposited around to make this kind of 3% iron on this hollow silicalite. And we can see that this system finally are very interesting because we have this specific void volume inside and small, very regular iron particles distributed in the borders of this hollow system. You can see that it's very stable systems on long-term testing under Fischer-Tropsch conditions. We can see how it's very stable. Again, after a long term, we can see that no major changes. While on conventional Fischer-Tropsch catalyst, we have big sintering occurring with the dispersion decreasing from 10 to 1%. And another point very important is that here, the production of CO2. With those catalysts, you see that the CO2, which is produced under Fischer-Tropsch conditions, is very low as compared to a conventional commercial Fischer-Tropsch catalyst. It means that with these hollow membranes around the iron particles, there is an effect of probably hydrophobicity, which decreases the water gas shift equilibrium, which deplays the water gas shift, and allow to save part of the carbon and less producing CO2, which is without any interest. So, and hydrophobicity. We have also some oil absorption, oleophilic, whatever. So we can extend this to other large chlorosiolites, like even with the riziolites. Like I've shown you the alkalization. There is now other techniques to create this mesoporosity for this chemical. So I will conclude here and wrap up. Indeed, for the science it's okay if you have enough. I would really insist on this pleasure and this stimulating personal collaboration with your institute since 20 years at least. 23 more, and hopefully we'll continue a little bit. We had a joint laboratory with our group, which has been several times confirmed now it's Strasbourg. Yeah. And indeed we have a deep friendship with big list.
Everybody knows.
Yeah.
Who is that?
You know that very by heart. And I will just finish by just an example of a fruitful collaboration between two champions of the chemistry. And what was very impressive is that even 100 years later, we are still working on this so-called Fischer-Tropsch synthesis, sure. And probably it will continue for years. So it's a very good example we have to take in mind. And so my wish is that other possibilities like Hans Salikov and Hans Mirodatos could also make for the future, because we have already some joint papers.
22,
joint
yeah.
papers. So I wish you all the best for this anniversary of your big institute and famous institute, and thank you for your attention. Thank you.